Dear students, welcome back. In previous class, we discussed about the linear congruences. That's the solution of a polynomial congruences. F of x congruence to 0 mod m is a solution. So, by using that idea, we goes to a theorem. Assume a and m are relatively primes to each other. Then the linear congruence Ax congruence to B mod m has exactly one solution. If A and m are relatively primes, then the linear congruence Ax congruence to B mod m has exactly one solution. How? Here consider this linear congruence Ax congruence to B mod m. So here we need to test the numbers 1, 2, etc. up to m. Why? Because the set 1, 2, etc. up to m always constitutes a complete residue system mod m. We say that the set of numbers 1, 2, etc. up to m always constitutes a complete residue system mod m. Therefore, their multiples, that is a, 2a, etc. ma also constitutes a complete residue system module. Complete residue system module. That also forms a to a, etc. ma forms complete residue system module. Then, therefore, exactly one of this product is congruent to, therefore, exactly one of these multiples, exactly one of this product is congruent to B mod m. Now, if there exists AR and exactly 1. So for if there exists AR and AS such that AR congruence to B mod m and AS congruence to B mod m. AR congruence to B mod m and AS congruence to B mod m. That means AR minus AS congruence to 0 mod m. AR minus AS congruence to 0 mod m. That means AR equals AS. AR congruence to AS mod m. That means AR equals AS. That means there exists exactly one S. There exists exactly one S such that AX congruence to B mod m. AX congruence to B mod m. Thus, if A and M are relatively prime, then the linear congruence Ax congruence to B mod m has exactly one solution. Because we only consider this set 1 to etc. up to m, because that constitutes a complete residue system. Also we see that their multiples CA, 2A, 3A, etc. ma, their products also constitute a complete residue system mod m. Therefore, there exists exactly one of this product is congruent to B mod m. So for this exact one, there is the uniqueness. If possible, there exists AR and AS such that AR congruence to B mod m and AS congruence to B mod m. After some steps, we have there exists only one S such that AX congruence to B mod m. Agreed. Now come to a definition. Suppose A and M are relatively primes. GCD of A and M equals 1. Then the unique solution of the congruence. Then the unique solution of the congruence AX congruence to 1 mod m. AX congruence to 1 mod m is called the reciprocal of A. It is called the reciprocal of A mod m. It's an important definition. Consider the unique solution of the congruence. The unique solution of the congruence Ax congruence to 1 mod m is said to be the reciprocal of A mod m when A and m are relatively prime. That is, if A dash be the reciprocal of A mod m, then if A dash be the reciprocal of the congruence A mod m, then B A dash is the solution of Ax congruence to B mod m. Then B A dash forms the solution of the linear congruence Ax congruence to B mod m. How? A dash be the reciprocal of A mod m means A dash congruence to 1 mod m. Why? Because of the definition. The Ax congruence to 1 mod m has a unique solution. If A dash be the reciprocal, then A dash congruence to 1 modium. A dash congruence to 1 modium means A dash into B congruence to B modium. Okay. A dash congruence to A dash B is congruence to B mod M means A dash B equals B A dash. So B A dash be the solution of the linear congruence AX congruence to B mod M. Agreed. Now again consider the A and M, that is GCD of, suppose GCD of A and M is D, means A and M are not relatively primes. Let A and GCD of A and M is D. Then the linear congruence AX congruence to B mod M. Then the linear congruence AX congruence to B mod M has solutions if and only if D divides B. A and M are not relatively primes, means they have a GCD, let it be D. Then the linear congruence AX congruence to B mod M has solutions if and only if D divides B. So come to the proof. It's necessary argument. First suppose that GCD of A and M is D. It is given GCD of A and M is D. First suppose that AX congruence to B mod M has a solution. AX congruence to B mod M has a solution. Let it be X naught. So what is it? That means AX naught congruence to B mod M. Agreed. AX naught congruence to B mod M means M divides AX naught minus B. Okay, M divides AX naught minus B. But what is D? D is GCD of A and M. That means D divides A and D divides M. So M divides AX naught minus B and M D divides M. That combinedly gives D divides AX naught minus B. So that means D divides B. Why? Because D divides AX naught. D divides A, that gives D divides AX naught. Therefore, D divides B itself. Hence, when AX congruence to B mod M has a solution, then surely D divides B. Okay. What about the reverse inclusion? Suppose that let D be the GCD of A and M, and suppose D divides B. Let AX congruence to, consider the linear congruence, AX congruence to B mod M. Then we have to show that this AX congruence to B mod M has a solution. AX congruence to B mod M, that means then since D is GCD of A and M, so clearly A by D and M by D are relatively primes. Okay, therefore here A by D X congruence to B by D mod M by D. A by D X congruence to B by D mod M by D. So this one has a solution. Agreed. Okay, that's a linear congruence. Then A by dx congruence to B by D mod M by D has a solution. Let it be X naught. Let this solution be X naught. That means A by D X naught congruence to B by D mod M by D. B by D mod A by D X naught congruence to B by D mod M by D. That means clearly A X naught congruence to B mod M. Okay, yes. Multiplying product by D, so it is Ax naught congruence to B mod M means X naught to be the solution of the linear congruence Ax congruence to B mod M. So the reverse inclusion is also finished. When D divides B, then consider Ax congruence to B mod M. Since D be the GCD of A and M, A by D and M by D are relatively primes, then surely A by dx congruence to B by D mod M by D, then this equation has a solution. Let it be X naught. That means A by dx naught congruence to B by D mod M by D. Then you can multiply product by D. That means X naught congruence to B mod M. That means X naught congruence to B mod M means X naught to be the solution of the linear congruence Ax congruence to B mod M. That is what we reduce here. Okay. Right. Now let us discuss another theorem. That's an important one. So the theorem states that assume GCD of A and M is D. GCD of A and M is D. And suppose that D divides B. Suppose that D divides B. Then the linear congruence AX congruence to B mod M has exactly D solutions mod M. Then the linear solutions AX congruence to B mod M has exactly D solutions mod M. D solutions mod M. They are given by T. The solutions are given by T plus M by D, T plus 2 M by D, etc. T plus D minus 1 M by D. T plus D minus 1 M by D. Where T is the solution, unique modulo M by D of the linear congruence A by D. T be the solution of unique modulo M by D of the linear congruence A by dx congruence to B by D mod M by D. B by D mod M by D. So this is the theorem. If A and M are, you see A and M has common factor D and D divides B, then the linear congruence AX equals congruence B mod M has exactly D solutions. In the previous theorem, we proved that when A and M is GCD of A and M is D and D divides B, then the linear congruence AX congruence B mod M has solutions. We already proved that when A and M GCD of A and M is D and D divides B, we see that AX congruence to B mod M has solution. Here we have to show that it has exactly D solutions is of the form T plus M by D, T plus 2 M by D, etc. T plus D minus 1 M by D. Then these D solutions, there exist exactly D solutions congruence to mod M, D solutions mod M. And T be the solution unique modulo M by D of the congruence, linear congruence A by dx congruence to B by D mod M by D. How to prove this one? The proof is done. Every solution of A by dx congruence to B by D mod M by D is a solution of AX congruence to B mod M. That is, proof is every solution of A by dx congruence to B by D mod M be a solution of AX congruence to B mod M. Why? This is already proved. Why? If let x naught be a solution, let x naught be a solution of this equation 1. So what you get? It is A by D x naught congruence to B by D mod M by D. So if you multiplying throughout by D, we have A x naught congruence to B mod M. That means x naught be a solution of the linear congruence AX congruence to B mod M. All of these factors are done in the previous step, in the previous theorem. Agreed. So every solution of A by dx congruence to B by D mod M by D is also a solution of the linear congruence AX congruence to B mod M. Agreed. Then A by dx, consider this congruence A by dx congruence to B by D mod M by D. Now A by dx congruence to B by D mod M by D. Then what is A and M? GCD of A and M is D. A and M has common factor D. That means A by D and M by D are relatively primes. Agreed. Then there exists a unique solution of the congruence A by dx congruence to B by D mod M by D by the previous argument. There exists exactly one solution of the linear congruence. So the linear congruence has exactly one solution when A and, we already proved that when A and M are relatively prime, then the linear congruence AX congruence to B mod M has exactly one solution. Here GCD of A by D and M by D are 1 means A by D and M by D are relatively prime. Then according to that theorem, this linear congruence A by dx congruence to B by D mod M by D has exactly one solution. Okay, yes. Then that is A by D, let it be T. Let it be T. So we have A by D T congruence to B by D mod M by D. That means M by D divides A by D into T minus of B by D. Sure? Okay. That again implies M by D divides A by D into T plus M by D minus T plus M by D minus B by D. A by D into T plus M by D minus B by D. Okay? Yes. That means T plus M by D, that means T plus M by D be a solution of T plus M by D be a solution of A by D x congruence to B by D mod M by D. Okay. You see, even A and M are relatively prime. We already proved that the linear congruence Ax congruence to B mod M has exactly one solution. So, in the light of that argument, when A by D and M by D are relatively prime, the linear congruence A by D x congruence to B by D mod M by D has exactly one solution. Let it be T. Then we have A by D into T is congruence to that one. Then M by D must divides A by D into T minus B by D. But M by D divides A by D into T plus M by D also minus B by D. That means T plus M by D be a solution of A by D congruence to B by D mod M by D. Agreed. Then in a similar way we can show that T plus 2M by D is also T plus M by D is a solution, T plus 2M by D is a solution, etc. We can show that T plus D minus 1 M by D is also a solution of A by D x congruence to B by D mod M by D. Same argument. Therefore, we have T, we have T plus M by D, T plus 2M by D, etc. T plus D minus 1 M by D are the solutions of Ax congruence to B mod M, means there exist D solutions. There exist D solutions, let be T plus M by D, T plus 2M by D, etc. T plus D minus 1 M by D. So these are the D solutions of the linear congruence Ax congruence to B mod M. Okay. Now we prove that two of these are incongruent, or not two of these are congruent to mod M. Now we prove that no two of these are congruent to mod M, or two of these are incongruent to mod M. How? If T plus R M by D, R into M by D is congruent to, if possible, T plus R M by D is congruent to T plus S M by D mod, is T plus S M by D mod U. Now we see that there exist exactly D solutions. Now we have to show that no two of these are congruent to mod M, that is two of these solutions are incongruent to mod M. That is, if possible, T plus R plus M by D, T plus R plus M by D congruent to T plus S, T plus R M by D is congruent to T plus S M by D mod M. That means R M by D congruent to S M by D mod U. S M by D mod M. That means R M by D into D by M congruent to S M by D into D by M into mod M into D by M. You can multiply throughout by D by M. That means R congruent to S mod M. R congruent to S mod M. You can choose this R and S in such a way that R and S are chosen in such a way that 0 less than R less than D and 0 less than S less than D. That means modulus of R minus S. From here, modulus of R minus S strictly less than D. Okay. R congruent to S, from here R congruent to S mod M and modulus of R minus S strictly less than D. That clearly implies R equals S. Why? Because we already proved a theorem. If A congruent to B mod M and modulus of B minus M strictly less than 0, then A equals B. Okay. Then according to that argument, if R congruent to S mod M but modulus of r minus s strictly less than d, s by the s from the choice of r and s, then clearly r equals s. Therefore, two of the solutions are incongruence to modium, that is, no two of the solutions are congruence to modium. Agree. Now it remains to show that ax congruence to b mod m. B mod m has, now it remains to show that ax congruence to b mod m has no solution. Okay. So how? No solution except these d solutions. Now we show that the linear congruence ax congruence to b mod m has no solution other than these d solutions. How? If possible, let y be the solution. Let y be the solution of ax congruence to b mod m. That means ay congruence to b mod m. Ay congruence to b mod m. We have t is a solution. Also, we know that from these solutions we have t be a solution. Let us consider t be a solution of this congruence, this linear congruence ax congruence to b mod m. That means at congruence to b mod m. Agreed. We have ay congruence to b mod m and at congruence to b mod m. That means what I get? Come on. Ay minus at or at minus ay, whatever may be. Ay minus at is congruence to 0 mod m. Enough. Ay minus at is congruence to 0 mod m. That means ay congruence to at mod m. Okay. Ay congruence to at mod m. Ay congruence to at mod m means, what about the GCD of a and m? Since GCD of a and m is d, we have y congruence to t mod m by d, since d be the GCD of a and m. So by the cancellation law, y congruence to t mod m by d, where d be the GCD of a and m. That means m by d is divides y minus t. That means m by d into k equals some y minus t, or y minus t equals m by d into k. Agreed? Okay. So y minus t equals k into m by d or m by d into k means y equals, so what is y? Y equals some k into m by d plus t, or t plus k into m by d for some k. But what is k? But k congruence to r mod d for some r satisfies 0 less than or equals r strictly less than d. K congruence to r mod d, where 0 less than or equals r strictly less than d. Therefore k into